Okay, today we'll talk about second order derivatives using Taylor series approximation. So let's get to second derivative approximations. Okay, let's remind ourselves of the Taylor series expansions. So we have f of xi plus delta x equals f of xi plus delta x, first derivative, or xi plus delta x square divided by 2 factorial f second derivative at xi plus delta x cube 3 factorial f third derivative at xi, and this series keeps going on. Okay, I had called this expression as 1. We can also write f of x at a small neighborhood before xi, f of xi minus delta x f1 xi plus delta x squared 2 factorial f2 xi minus delta x cube divided by 3 factorial f3 xi, and so on. So let's call this 2. Okay. Now, in order to attempt to get the second derivative, I notice that f2 is right here, and I don't want the first derivative, so I don't want these terms. So what I can do is I can sum 1 and 2, and by summing you'll see that this term involving the first derivative will actually cancel out. So let's do that. So sum 1 with 2 to get f of x I plus delta x plus f of xi minus delta x equals 2 f of xi. That's the first term. The second terms cancel off with each other. The third term is it's 2 factorial is 2, so delta x square f2 xi. The fourth term will cancel, and then we'll have the fifth term will be x4 4 factorial f4 xi plus so on. Now what I'm going to do is I'm going to move things around and write a formula for f2 x squared, and I'm also going to divide by delta x squared, so I'm only left with f2 xi. So f2 xi, which is the one which is highlighted there, equals f of xi plus delta x plus f of xi minus delta x. I move this to the left, so 2f of xi divided by delta x square, which is this one. And then I need to divide this also by delta x square, so I'll be left with yeah, so this goes on the other side, so it'll be minus 2 delta x square 4 factorial f4 xi. Now, if I assume that terms involving x square and above are small enough that I can ignore them, then I can just get rid of, we'll assume that these terms and additions are negligible. Okay, this is where the approximation comes after all, so we can ignore them. And so a formula for the second derivative is going to be f2 xi equals f of xi plus delta x plus f of xi minus delta x minus 2f of xi divided by delta x square plus the truncation is of order delta x square. So this is the truncation error of delta x square. Okay, so this is the formula which we will be using to compute the second derivative. This formula is also known as a 3-point central difference second derivative approximation. It's called 3-point because you use 3 points: f of x plus delta, f of x minus delta, and 2, and f of xi. And then it's called central difference because it sort of takes the corner points x plus delta x, but it also uses the middle point. So it's using this 2 points and the middle one. So it's sort of uh, using the center point and the sideways point. That's why it's called central difference. Now you could also derive other expressions for the second derivative, and I'll write 2 more of these expressions, and I will leave it to you to figure them out. So similarly, we can show that f2xi is f of xi plus delta x, sorry, 2 delta x minus 2 f of xi plus delta x plus f of xi, the whole thing divided by delta x square, plus the error here is of the order of delta x, which is inferior to what we derived because that our error was of the order of delta x square. And here's another formula: f of xi minus 2 xi minus delta x plus f of xi minus 2 delta x, and this divided by delta x squared. This is order is also of the order of delta x. Now these formula are known as the 3-point forward. The first one is the forward difference. The second one is the backward difference. Backward second derivative approximation. It's 3-point because it uses 3-point, and it's forward backward because it's just the way the points are. It only uses points forward of xi, so xi plus delta x and xi plus delta x. And this one is called, the second one is called backward because it only uses points behind xi minus delta and xi minus 2 delta x. Now there's a series of formulas which I wouldn't go into deriving, but you can derive if you want, but you might have problems involving them. Here are some approximations. This is forward difference approximation. This is the first derivative. This is the second derivative, third and fourth. Here f2 is the same as f double prime, and f3 is the same as f triple prime. Okay, and when they say fi, it means f of xi. If they say fi plus 1, it means f of xi plus delta x. If they say f of I plus 2, it means f of xi plus 2 delta x, and so on. Okay, so these are formulas for the first 4 derivatives, and you can see it uses, this one uses 2 points, this one uses 3 points, this one uses 4 points, this one uses 5 points. And that's forward difference. It's accurate delta x. This is a forward difference, but it's more accurate. So this is more accurate, more accurate than order delta x. Okay. So here are formulas. You can see that, for example, for the first derivative, this one uses 2 points, but this one, to get more accuracy, it is using 3 points, and so on. So the first 4 derivatives. Okay, then we have, these are only backward difference approximations of different orders. So again, you'll see they have a trend similar to forward difference. Then we have central difference. Okay, this is accurate to delta x square for the first 4 derivatives, and this is actually remarkably more accurate, as its order is delta x raised to 4. Again, it has 4 derivatives. You can see that the number of points increases as the accuracy, as you want to increase the accuracy. So 2 points here versus 4 needed for this accuracy. So this is more accurate than the former. So order delta x square. Okay, so with that, we can now try to apply this on some problems. So here is a problem related to what we just did. So problem, so continuing from previously, this will be problem 4. Compute the second derivative of tangent of x at x equals pi divided by 6 using 1 3-point central difference, three-point forward difference, three-point backward difference. Okay, and I might want to add that let's just stick around with an approximation which is accurate to delta x square. Okay, so accurate to order delta x square. Okay, so note that we also have delta x raised to 4. And also, you're given the step size. Use a step size of 1e negative 2 and 1e negative 4. And of course, compare against the actual value. So you want to do the first, the easy part first, which is actually get the actual value. So let's do that. Y is tan of x, dy by dx is secant square x, and then d square y by dx square. In order to do this, what you need to do is you can use the chain rule, or if you know the derivative of secant square x, well, let me use the chain rule. So for the chain rule, I first find the derivative of secant square x. So that derivative is secant x. So that's the derivative of something like x squared, it'll be 2x. So it's 2x or 2 secant x. And then we need to find the derivative of just secant x. That will be secant x tangent of x. Okay, so if you want to find or compute the derivative of d by dx squared, x equals pi divided by 6, all you do is put x equals pi divided by 6, and you get 1.5396. Okay, that's our true value. Okay, now let's start doing using the formula. So we have 3-point central difference. 3-point central difference. So let's go back to central difference. And we are told that we want to be accurate to delta x square. The formula we are interested in is, well, in this case, we want the second derivative. And so this is the formula we need to use. So I'll write that down. x plus delta x plus f of x minus delta x minus 2 f of x divided by delta x squared. Okay, the next one in the list is 3-point forward difference. So again, we go back to this. We are in central difference. Well, sorry, we are in forward difference. Forward difference, we're looking at order of delta x squared. And so in my notes, I should have put this better. So this was order delta x squared. This should be order delta x, and this should be order delta x. My bad. So this should be what I wanted. So order delta x. So if you go forward difference, we want to order delta x. We want the second derivative, and so we want this formula. Okay, so we'll write that formula down. F of x plus delta x, sorry, 2 delta x minus 2 f of x plus delta x minus 2 of minus f of x divided by delta x squared. And then, so this, by the way, I should put it here, this is of the order of delta x squared. This one is the order of delta x. And then third one is 3-point backward difference. So again, we go to the backward difference. We only want order delta x. And here we are looking specifically at second derivative. So I'll write this formula down. So if I, let me put that down. So it's going to be f of x minus twice f of x minus delta x plus f of x minus 2 delta x divided by delta x squared. So what remains to be done is we need to put x equals pi divided by 6. We need to take delta x as 1e negative 2 and 1e negative 4, put in the formula, and then get the corresponding answer. So what I did was I did that calculation. So 3-point central, 3-point forward, 3-point backward, and I use different step sizes. So with 3-point central difference, I get 1.53997 into 4 decimal places, 1.5940, 1.4873, 1.5396, 1.5401, 1.5390. Okay, now comes the part where we check true value. True value is right here, 1.5396. So let's go and check this out. Okay, so 1.5396 looks like this checks out. 5397, that's close. So using 3-point central difference, which by the way was accurate to delta x, where we get exactly the value we wanted. However, if you use 3-point forward and 3-point backwards, which is accurate to delta x, you see that delta x squared gives you much higher accuracy. So one way of having high accuracy is to use a kind of approximation which has lower truncation order.